Okay, so we're going to pick up here from the last video, and we have the whole situation just summed up here. So we made a random variable to measure the time it takes for the distance it takes for 4 flaws, and that is a gamma distribution because it's multiple events in a fixed lambda time interval or average rate. And in order to solve this problem, basically what we did was we changed it. We did a long process of changing it to a Poisson and looking at it from a Poisson problem, and then working it out this way. Okay, so what I want to do now is I want to try to take this specific problem. So I estimated the answer after a calculator. It's about 16% probability that there'll be 4 flaws in 25 meters of cable. Okay, so let's try to generalize, and so we can have a general equation just to solve any gamma distribution. Okay, so first of all, let's generalize this line. This was, going back to originally, this was R, was the 4, and this 1/12 was from lambda. Now lambda of the underlying exponential function, distribution, sorry, underlying exponential distribution, and the unit rate of that exponential function. Okay, this 25 was, we're trying to measure whether the time is going to take, or the distance is going to take less than 25 meters. So if the distance that was this line here, what we're trying to find. If we're generalizing that, then t can just be less to some x, some value x. In this specific case, our little x is the 25 meters. Okay, so let's look more about where these are coming from here. Where does this 2.1 come from? Okay, so going back to when we originally found this 2.1, we took this value of x, the little x, of how much time it's going to take, and we multiplied it by this unit rate. Okay, so this 2.1 came from multiplying this little value here, which was the 25, with lambda. Okay, so this in general would be the Poisson distribution of lambda x, little x. Now, no, there could be a little confusion here. I'm using the little x here, and the reason why is because later down the line, this little x is going to be for the cumulative distribution function, because basically that's what actually we calculated here, right? We calculated this, the cumulative distribution function, the probability that t is going to be less than some fixed value. Okay, and okay, so this is lambda t. Let's keep going through here. Okay, so let's generalize here. This was for 4, but where did that 4 come from? That actually came from up here, but this in terms of our variables that we named already, it's r, right? R is the number of events that we're measuring in terms of. So we're measuring in terms of 4 flaws. Okay, so this right here generalized was this r. And okay, so this 2.1 note, so let's go down to here, because this is where we're interested. This is the formula part worked out. I'm going to take one step first to just wrangle up all of these expanding summations here and just express it as a summation. Okay, so we could say that this was e to the, well, I'm going to generalize, start generalizing right away, because this 2.1, we already have it. It was the lambda in the Poisson is the lambda x here. So this is negative lambda x. Okay, what is this? Well, this is a summation. And this summation iterates. Notice the values that are iterating are this exponent here and this term in the denominator here. They're each going up 1. And if we can just count add up, that's what the summation means. We're going to add up all of those terms as they iterate through these values. So I'm going to use I to represent this value that we're iterating through. And it starts at 0. This is saying that we're starting at I is going to equal 0. And then where are we going up to? Where does this 3 relate in terms of up to here? So recall that when we switched this to 1 minus the complement, then this became 3. Now, in general, that could have been, if we're being more general, it will always just be, we got 4 from 4 minus 1. It's the next lower one. So if we're being more general, it's going to be r minus 1. We took this number, and the complement of x plus x greater than or equal to 4 is x, big X, less than or equal to 3, but the 3 just came from subtracting 1, so that's what I did here, subtracted 1. And then I just need to write this in terms of I, because this is what I'm using here. Oh, and also the 2.1. The 2.1, remember, is lambda x in general. Lambda x to the I over I factorial. Okay, there's your equation for the cumulative distribution function of the gamma function. Now, I should note this is only for when r is an integer. Now, in general, r does not have to be an integer, and there are applications where r is not an integer, but it always is a positive number. And for our cases, we're only going to look at the integer cases. And in this case, and in all the cases that we'll look at, it wouldn't really make sense to have r not be an integer. It depends on what you're modeling, of course. So in this case, flaws, well, 4.3 flaws would be a strange thing to care about. But there are cases where it could be. Okay, so let's write that formula out. If we have exponential, so if we have a gamma distribution r lambda, then our cumulative distribution function, which is the more useful one, is, and just to quickly refresh ourselves, it's always the same as equivalent to this, but our equation was 1 minus e to the negative lambda t summation from I equals 0 to r minus 1 of the lambda little x to the I over I factorial. And now let's use this to solve a problem. Oh, actually, before I do that, let's go over quickly some of the important things. So if this is gamma distribution, what does its mean? Well, that's going to be r over lambda. And its variance is going to be r over lambda squared. Okay, so in this case, directly follows from exponential function. You're just multiplying the exponential function's mean by r, and same with the variance. Okay, so I'm going to answer now a question that came on the classwork. We didn't actually get to doing it in the classwork, so I'll just do it for you now. And it basically comes down to just using these equations. Okay, so we were given this specific gamma function where gamma is 4 and lambda is 0.5. And the first thing we were asked for is the standard deviation. Okay, so that part is going to be very easy. We just plug in the values we have been given, and we get 8, and same deal over here. 0. Okay, so we have a mean and variance, and of course we could easily get the standard deviation as 4 as well. Okay, and then lastly, so it's a pretty quick question here. This is part A, it's part B, and then part C. We want to find the probability that t is less than or equal to 1. Okay, and real quick, this is the same as this is just another way to write this, the cumulative distribution for 1. And we have the cumulative distribution up here. However, it's got all these variables in here. Now note, we don't have to find what I is. I is just the iterator, so that just goes here. But we do have to fill in the variables for all of these. So let's just make sure we know what, we know what lambda is. That's clear. R, we also know what that is. We used it over here. R is 4. So that follows just straight from the description and the distribution. The last one we need to know is what this little x is, and of course the little x is just 1 in this case. Okay, so little x is what you would put here, or you would put here into the cumulative distribution function. So we have everything we need to fill in the formula. Give me some space here. 1 minus e to the lambda x. We might as well just multiply those. So lambda times x, well, x is just 1, so it's just negative 0.5, and this goes to 0, and now it's going to go up to r minus 1. R is 4, so we get 4 minus 1 is 3, and then we can fill in our value for lambda x, which is 0.5. This is still iterating through these. And we would have to write this out at this point. At this point, the only way to calculate this directly, unless you have some software or something, or some application, is to just write these out, just write out the iterators. So I need some more space to do that. It's going to be 1 minus, and when you work that out, I get something really, really small, actually rounding, so hey, so there we oh, I changed that 2%. Okay. There we go. That's how you apply the lambda function equation. There it is. Good thing you don't need to memorize it, but you do need to know where all these variables are coming from, and you would have to know how to interpret a question correctly to model it in this term, and then use the